In this video, we examine damped oscillations in more detail and derive the differential equation that describes such oscillations. To illustrate the concept, we consider the oscillation of a spring pendulum. In an idealized, undamped oscillation, the amplitude remains constant over time. In reality, however, every oscillation is damped due to frictional effects, causing the amplitude to decrease over time. The damping is caused, for example, by air resistance. We can investigate the influence of friction on the oscillatory behavior by placing the spring pendulum in a glass tube and filling it with liquids of different viscosities. When water is used as the friction medium, a significantly stronger decrease in amplitude over time becomes apparent. As the viscosity of the medium increases, for example when alcohol is used instead of water, the damping also increases, and the amplitude decreases more rapidly. As we will see later, when the damping is proportional to the velocity, the decrease in amplitude follows the behavior of an exponential function. In such cases, the amplitude therefore decreases exponentially. We can increase the damping of the system even further by using a highly viscous oil as the damping medium. In this case, the spring pendulum is so strongly damped that only two complete oscillations are visible before the system comes entirely to rest. The illustrated oscillation curves show that despite the strong damping, the period duration is barely affected. When we examine the magenta-colored oscillation curve, in which the system performs only 4 visible oscillations before coming to rest, we see that the period duration has changed only minimally relative to the undamped oscillation. If the period duration of the undamped oscillation is exactly 1.00 seconds, it increases by only about 2% to 1.02 seconds in the case of the magenta-colored curve, despite the strong damping that allows only 4 visible oscillations. Only under extreme damping, as shown in the green oscillation curve with just 2 complete oscillations, does the period duration increase significantly. In this case, it has increased by about 16% to 1.16 seconds. So note, only when the damping is very strong, typically when the system performs fewer than 5 visible oscillations, does the period duration increase noticeably relative to the undamped oscillation. In contrast, under moderate damping, this increase is so small that it can often be neglected in practice. If the damping is increased further by using an even more viscous medium, the period duration continues to increase significantly. From a certain level of damping, known as the critical damping, for example when using a very viscous medium such as honey instead of oil, the period duration becomes infinitely large. The system no longer exhibits oscillatory behavior. The body then moves toward its equilibrium position without oscillating around it. In this situation, the process is no longer an oscillation in the classical sense, which would be characterized by periodic motion around an equilibrium position. This limiting case, in which no oscillatory behavior occurs due to critical damping, is referred to as the aperiodic critical case. In principle, we can continue to increase the damping of the system, for example by using a highly viscous grease. Above the level of critical damping, the motion becomes a slow creeping toward the equilibrium position, which simply takes more time as the damping increases. These cases are referred to as overdamped. An especially important case in practice is the critically damped one. It returns the system to its equilibrium position in the shortest possible time, even faster than the oscillatory cases. The aperiodic critical case is therefore particularly important in devices such as shock absorbers. When critical damping is present, the system returns to equilibrium as quickly as possible. That is the whole purpose of shock absorbers, to ensure that a vehicle returns to its equilibrium position quickly after a disturbance, without beginning to oscillate. To describe the oscillation of a damped system, we will derive the differential equation for the spring oscillation as an example. With its help, the corresponding equation of motion can then be verified. As usual, we place the coordinate system in which we describe the motion at the equilibrium position of the spring system. The derivation of the differential equation follows the standard procedure, namely by drawing a free body diagram. For this purpose, we consider the mass in an arbitrary positive position of the coordinate system while it moves downward in the positive direction. At a distance s from the equilibrium position, the position-dependent spring force Fs acts on the body. As is well known, this force can be described using Hooke's law. Since the spring force always acts in the direction opposite to the displacement, this is expressed mathematically by a negative sign. Note that the weight of the mass has already been fully compensated by the static displacement that defines the equilibrium position and therefore does not need to be considered separately. This was explained in detail in the video about the vertical spring pendulum. In addition to the spring force, a frictional force Ff now acts on the body. This force depends on the velocity v. It always acts in the direction opposite to the motion and tends to slow it down. In many cases, a proportional relationship between frictional force and velocity can be assumed. The damping constant k describes this proportionality between force and velocity. It is essentially the counterpart of the spring constant. While the spring constant describes how strong the spring force is for a given displacement, the damping constant describes how strong the frictional force is for a given velocity. That the frictional force depends on velocity is something we know from everyday experience. For example, when we move our hand slowly through water in a swimming pool, we feel only a small resistance. However, if we move the hand quickly, the resisting force becomes noticeably larger. The frictional force therefore depends on the velocity with which we move an object through a medium. Since the frictional force is always opposite to the velocity, this is also represented in the formula by a negative sign. The total restoring force acting on the body is the sum of the spring force and the velocity-dependent frictional force. This yields the corresponding formula for the restoring force. According to Newton's fundamental equation, this resulting force causes an acceleration a of the mass m. This leads to the given equation. In this equation, the acceleration a, the displacement s, and the velocity v are time-dependent quantities. We indicate this time dependence by writing them as functions of time. These quantities, displacement s of t, velocity v of t, and acceleration a of t, are not independent of one another but are linked by the first and second time derivatives. If we express the acceleration as the second time derivative of the displacement function and the velocity as its first time derivative, we finally obtain the differential equation of the damped oscillation. What is the solution to this differential equation of the damped oscillation, and thus the corresponding equation of motion that can be used to describe such a damped oscillation? The classical equation of motion of an undamped harmonic oscillation is generally no longer a solution of the damped differential equation, since it does not account for a decrease in amplitude. The constant amplitude Smax is therefore replaced by an exponential approach of the general form a times e to the power of minus delta times t. This function ultimately represents an envelope curve, where a is an initial condition and delta is the so-called decay constant, since this factor essentially describes the decay of the amplitude. It can be expected that the decay constant delta is related to the damping factor k, because the greater the damping, the stronger the decay of the amplitude. The indicated possible solution of the differential equation therefore consists of a combination of a time-dependent exponential function, which describes the decrease of the amplitude over time, and a time-dependent sine function, which describes the periodicity of the oscillation, that is, the repeated back-and-forth motion. The specific values that the quantities a, delta, omega, and phi 0 take, and whether this equation of motion is indeed a solution of the differential equation, can only be verified by substituting the proposed equation of motion into the differential equation. To verify the solution using the differential equation, we need both the first and the second derivative of the possible displacement function. In this case, we must apply both the product rule and the chain rule. We first apply the product rule to the exponential expression marked in blue and the sine expression marked in red. We first differentiate the exponential expression marked in blue, while leaving the sine expression marked in red unchanged. The derivative of the outer exponential function gives the exponential function itself. This is then multiplied by the derivative of the inner function, which is the exponent minus delta times t with respect to time t. This results in minus delta. The sine term marked in red remains unchanged. Next, we leave the exponential expression marked in blue unchanged and differentiate the sine term marked in red. The derivative of the outer function produces a cosine function, while the derivative of the inner function, which is the argument of the sine function, gives the value omega. We can now factor out the exponential expression marked in blue and finally obtain the specified function for the first derivative. We now need the second time derivative of the equation of motion. This means that we must differentiate the first time derivative once more. The procedure is essentially the same as before. Again, we apply the product rule to the exponential expression marked in blue and the combined sine and cosine expression marked in red. We start again by using the chain rule to differentiate the exponential expression marked in blue, leaving the sine and cosine terms marked in red unchanged. This gives the expression shown. We then leave the exponential term unchanged and differentiate the sine and cosine terms marked in red by applying the chain rule. Altogether, we obtain the expression indicated. Here as well, we can factor out the exponential term marked in blue, thereby obtaining the required second time derivative of the equation of motion. We now substitute the equation of motion along with its first and second time derivatives into the differential equation. This initially results in a relatively long equation. In this equation, however, the exponential terms can be cancelled. We then expand the term marked in red within the brackets and obtain the equation shown. After that, we move all terms marked in red from the right-hand side to the left-hand side of the equation, which changes only their signs and ensures that the entire expression must equal 0. We then rearrange the equation by factoring out the sine term marked in red and the cosine term marked in blue. In this way, we obtain the compact equation shown. How should this equation be interpreted? The right-hand side of the equation is clearly 0. On the left-hand side, however, we have a sine term and a cosine term, which are generally not 0. Consequently, the left-hand side can be 0 at all times only if the two bracketed expressions are themselves 0. If these bracketed terms were not 0, the left-hand side of the equation would not equal 0 at all times due to the sine and cosine terms. But this must be the case, according to the equation. Therefore note, since the differential equation must be satisfied at all times t, this is only possible without contradiction if the expressions within the brackets are 0 for all times. From these conditions, we can now determine the decay constant delta. If we set the bracketed expression marked in blue equal to 0, the decay constant delta results as the quotient of the damping constant k and twice the mass m. Furthermore, the angular frequency omega can be determined by setting the bracketed expression marked in red equal to 0. In doing so, we use the previously derived expression for delta. This yields the stated formula for the angular frequency omega. This expression can be simplified further. The term marked in blue corresponds to the decay constant delta. In addition, we have seen in the video on the undamped spring oscillation that the undamped angular frequency omega 0 corresponds to the square root of d divided by m. Therefore, the quotient of the spring constant d and the mass m corresponds to the square of the undamped angular frequency omega 0. If we replace the quotient of spring constant and mass with the square of the undamped angular frequency omega 0, we obtain the stated formula for determining the angular frequency of the damped oscillation. Thus, the angular frequency omega of the damped oscillation can be expressed in terms of the undamped angular frequency omega 0 and the decay constant delta as indicated. At this point, we can already see that the oscillation frequency of the damped oscillation omega is always smaller than the frequency of the undamped oscillation omega 0, because the decay constant delta reduces the oscillation frequency. As long as the damping constant k and therefore the decay constant delta are smaller than the angular frequency omega 0 of the undamped oscillation, the expression under the square root is positive. This gives us a mathematically and physically meaningful value for the angular frequency omega of the damped oscillation. These cases are referred to as the underdamped cases. With increasing damping, however, the decay constant delta becomes larger and larger, causing the angular frequency of the damped oscillation to decrease and the period to increase. In the extreme case, the decay constant delta can even become larger than the angular frequency of the undamped oscillation. The expression under the square root, the so-called discriminant, then becomes negative and no real solution exists. In such cases, the motion is no longer oscillatory but represents overdamped cases, which can no longer be described by the previous equation of motion. The critical case in which the discriminant becomes exactly 0 and the decay constant delta therefore equals the angular frequency of the undamped oscillation omega 0, corresponds to the critically damped case. Now that we have determined the decay constant delta and the angular frequency omega, we still need to determine the quantities a and phi 0 in the equation of motion. These quantities follow from the initial conditions. Here, we consider the case in which the body is released from the displaced maximum position Smax at the time t equals 0 without any initial velocity. Since the first derivative of the displacement function corresponds to the velocity, the first derivative must also be 0 at the time t equals 0. Substituting t equals 0 into the first derivative yields the corresponding expression. We rearrange this equation as indicated. The quotient of the sine function and the cosine function corresponds to the tangent function. The tangent of the angle phi 0 is therefore equal to the quotient of the angular frequency omega and the decay constant delta. Thus, the given expression holds for the angle phi 0. We now need to determine the value a in the displacement function. This value follows from the initial condition that the displacement function must have the maximum value Smax at the time t equals 0. The value A therefore results from the quotient of the initial maximum displacement Smax and the sine of the angle phi 0. For the angle phi 0, we can insert the previously derived expression. A look into a mathematical reference shows the given relationship, so that the green-marked sine term can be replaced by the corresponding square root expression. This yields the overall expression for the value A. Note that these formulas for determining the quantities A and phi 0 only hold in this form if the body is released from rest. If the body already has an initial velocity at the time t equals 0, for example because it is pushed, these formulas no longer apply. Furthermore, it is important to understand that the value A is generally not equal to the initial displacement. The initial displacement is Smax. The quantities A and phi 0 are mathematical constants that must be determined from the given initial conditions. We have now determined all quantities that are required to describe a damped oscillation. Let us consider an example. A spring has a spring constant d equal to 3.14 newtons per meter. Attached to it is a sphere with a mass m equal to 79.6 grams. The mass of the spring can be neglected in comparison to the mass of the sphere. The damping constant is k equal to 0.1 newton-seconds per meter. The sphere is displaced from the equilibrium position by the distance Smax equal to 10 centimeters and then released. With these quantities we can completely describe the damped oscillation. To do this, we determine the initial amplitude A, the initial phase angle phi 0, the angular frequency omega, and the decay constant delta. For calculating the angular frequency omega we need not only the decay constant delta, but also the angular frequency omega 0 of the undamped oscillation. This results from the square root of the ratio of the spring constant d to the mass m. After inserting the values, we obtain an undamped angular frequency of 6.28 radians per second. Since the angular frequency omega 0 is linked to the oscillation frequency f0 by the formula omega equals 2 pi times f, we can determine the oscillation frequency of the undamped oscillation. It is f0 equal to 1.00 Hz. The reciprocal of this frequency yields a period of the undamped oscillation of t0 equal to 1 seconds. Now we determine the decay constant delta according to the given formula. After inserting the damping coefficient k and the mass m, we obtain delta equal to 0.63 radians per second. With the undamped angular frequency omega 0 and the decay constant delta, we can now calculate the angular frequency omega of the damped oscillation. Inserting the corresponding values yields an angular frequency of omega equal to 6.25 radians per second. Using the relationship omega equals 2 pi times f, we obtain an oscillation frequency f equal to 0.995 Hz. The reciprocal of this frequency yields a period t equal to 1.005 seconds. Compared to the undamped oscillation, the period has therefore increased by only 0.5%, even though a relatively strong damping is already present. This shows that in many practical cases, the increase in the period of damped oscillations can be neglected. We now determine the initial phase angle phi 0 using the given formula involving the angular frequency omega and the decay constant delta. After inserting the numerical values, we obtain phi 0 equal to 1.47. This is the angle in radians and corresponds to approximately 84 degrees. Finally, we calculate the initial amplitude A using the given formula based on the initial displacement Smax, the decay constant delta, and the angular frequency omega. After inserting the values, we obtain A equal to 0.1005 meters. We now have all quantities required for the equation of motion that fully describes the damped oscillation. If we plot the oscillation in a displacement time diagram, we obtain the curve shown. At this point, it should again be emphasized that in the equation of motion, the exponential term preceding the sine function represents the envelope of the displacement function. This term describes the temporal decrease of the amplitude. Furthermore, it must be noted that the quantity A, referred to as the initial amplitude, is greater than the initial displacement Smax. One might therefore initially assume that the amplitude at the beginning of the oscillation is greater than the maximum displacement. However, this is not the case, because this apparent contradiction is compensated by the initial phase angle phi 0. To illustrate this, let us consider the displacement function at the beginning of the oscillation, that is, at time t equal to 0. If we insert t equal to 0 into the function, the exponential function becomes 1, and the first term in the argument of the sine function vanishes. This yields the indicated expression for the displacement at the beginning of the oscillation. We see that although the initial amplitude A appears to be greater than the initial displacement S max, this effect is corrected by the sine term with the initial phase angle phi 0. Inserting the numerical values yields, at time t equal to 0, the correct initial maximum displacement S max equal to 0.10 meters. It should be noted that the exponential term, which describes the decrease of the amplitude over time, becomes smaller as time progresses and thus the amplitude continuously decreases. However, strictly speaking, it never reaches the value 0. In practice, there are therefore various approaches to define the complete decay of an oscillation. A common definition states that an oscillation is considered fully decayed when the envelope, that is the exponential term in front of the sine function, has decreased to 1/1000th of its original value. The amplitude of the oscillation has then fallen to 1/1000th of its initial value, and the system can be regarded as having practically come to a standstill. Let us now determine, for our oscillation according to this definition, the duration until the oscillation is fully decayed. We observe that the initial amplitude A cancels out in the corresponding equation. To solve the equation for the time t, we apply the natural logarithm function to both sides. Since the natural logarithm is the inverse function of the exponential function, we obtain on the left side of the equation the exponent of the exponential function, that is, the negative product of the decay constant delta and the time t. We then rearrange this equation to solve for the desired time duration t. After substituting the values, we obtain a time duration of approximately 11 seconds, after which the oscillation is considered fully decayed according to this definition. We have previously determined that the period of this oscillation is approximately 1 second. This means that the oscillating system practically comes to a standstill after about 11 oscillations. With the chosen damping coefficient K equal to 0.1 Newton-second per meter, this corresponds to a relatively strong damping. Let us now consider an even more strongly damped case, for example with a damping constant K equal to 0.5 Newton-second per meter. In this case, the period increases to 1.155 seconds, and the oscillation has already decayed after approximately 2.2 seconds according to our 1000th definition. The system completes in this case only about 2 oscillations. If we increase the damping constant further, for example to K equal to 0.9 Newton-second per meter, the period increases to 2.3 seconds, and the system does not even perform a complete oscillation. The question now is, at which damping constant does the system reach critical damping? As previously explained, this occurs when the discriminant in the formula for the angular frequency omega becomes 0, resulting in the period theoretically becoming infinitely large. Critical damping is reached when the decay constant delta corresponds to the angular frequency omega 0 of the undamped oscillation. By substituting the corresponding formulas and solving the equation for the critical damping constant K, we obtain the given formula. The critical damping factor corresponds to the value of 2 times the square root of d times m, and depends solely on the spring constant d and the mass m. With a spring constant of 3.14 Newton per meter and a mass of 79.6 grams, the critical damping factor is therefore 1.00 Newton-second per meter. In this case, the system no longer oscillates but merely creeps into the equilibrium position. Note that the previously given equation of motion is no longer applicable in this case. The displayed diagram shows the increase of the period with increasing damping constant up to the critical case, in which the period theoretically becomes infinite. For the oscillation cases shown in the upper diagram, the corresponding damping constants are indicated in the lower diagram for orientation. However, this diagram also makes it clear that for damping constants smaller than 10% of the critical damping factor, the increase of the period can often be neglected. Note, however, that even at 10% of the critical damping factor, there is already relatively strong damping, where the system, as previously observed, performs only about 11 oscillations. For these cases, the equation of motion of the damped oscillation can be formulated much more simply. Under the assumption that the period of the damped oscillation is approximately equal to the period of the undamped oscillation, this also applies to the corresponding oscillation frequencies. Therefore, in these cases, the angular frequency of the damped oscillation omega can be approximated as equal to the angular frequency of the undamped oscillation omega 0. According to the formula for calculating omega, this approximation is justified only if the decay constant delta is negligibly small compared to omega 0. That is, delta is much smaller than omega 0. Since omega 0 is approximately equal to omega, it follows that delta is also much smaller than omega. This relationship greatly facilitates the determination of the initial phase angle phi 0. If delta is much greater than omega, the quotient in the argument of the arctangent function becomes very large and theoretically infinite in the limit. In this case, the arctangent function yields the value pi over 2. The initial amplitude A can also be determined more easily under this assumption. If delta is much greater than omega, the quotient in the corresponding expression becomes very small. After squaring, the value becomes extremely small and approaches 0 in the limit. Under the square root, the value then becomes 1, so that the initial amplitude A corresponds to the initial maximum displacement Smax. These approximate values can now be substituted into the original equation of motion. With an initial phase angle of pi over 2, the sine function is phase shifted by 90 degrees, so that the cosine function can be used instead of the sine function. This results in the given equation of motion to describe a damped oscillation. In this function, only the angular frequency omega0 and the decay constant delta are required. It should be noted that in this approximated equation of motion, the exponential term in front of the cosine function no longer describes the envelope of the oscillation, but rather the course of the local maxima, that is, the progression of the amplitude. Finally, let us once again consider the differential equation of the damped oscillation. We derived this equation exemplarily for a spring mass system. However, there are other systems that perform damped oscillations, for example a simple pendulum. We therefore generalize the differential equation for any case in which the velocity-dependent frictional force is proportional to the velocity. The constant term in front of the displacement function, which in our example corresponds to the quotient of spring stiffness and mass, can generally be written as the square of the undamped angular frequency omega0. The constant term in front of the first derivative of the displacement function always corresponds, in damped oscillations, to twice the value of the decay constant delta. This is the general form of the differential equation of a damped harmonic oscillation.